Physicists recently cracked the black hole mystery after 50 years. Forget lost information. Jump into a black hole, and your body's details gradually resurface, challenging the old belief. String theory hinted at this, but recent calculations rooted in gravity and quantum effects independently confirm it. Gravity flips script. Info defies black holes, challenging Einstein. Recent studies unveil novel gravitational effects, unmasking black holes as open systems. Forget lost info, they swallow and spill secrets. The game changer? A nod to Hawking's semi-classical approach, revealing overlooked gravitational configurations. In the last 2 years, science hints at a breakthrough, unraveling the mysteries of these cosmic giants. In a recent breakthrough, Donald Marolf and his team from UC Santa Barbara, celebrated by Eva Silverstein at Stanford, achieved a milestone in black hole research comparable to Hawking's contributions. However, Geoff Penington from UC Berkeley expressed a sense of disappointment. While they successfully addressed the specific challenge of information escape from black holes, there's a yearning for deeper insights into quantum gravity. The cosmic quest for understanding continues. Scientists debate groundbreaking findings, exploring complex concepts like wormholes, holographic principle, and quantum mysteries. Skepticism persists, questioning Hawking's insights, while others champion string theory. Consensus leans to space-time disintegration at black holes, hinting at a deeper reality. In '92, during a Christmas vacation, physicist Don Page ponders black hole paradoxes tied to Hawking's realization. The challenge? Radiation lacks structure, unveiling a mysterious source within black holes. The black hole dilemma, suggesting irreversible formation and evaporation, clashes with quantum mechanics. Hawking and many accepted it, but in 1980, Page argued for information preservation. This divided physicists. General relativists sided with Hawking, while particle physicists favored Page. Page's insight during his vacation shifted the focus from just the black hole's end to its entire life cycle. The Blackhole Information Paradox expanded to consider not only its demise, but also the events leading up to it. In this, Page explored the neglected quantum entanglement aspect. Page's calculations tracked entanglement entropy, representing quantum link between a black hole and emitted radiation. Let's break it down. Entanglement entropy is like a quantum connection between a black hole and the radiation it spits out. At the beginning, it's at zero. If info sticks around inside the black hole, it should go back to zero at the end of its existence. Page kept tabs on how the radiation's entropy changes over time, uncovering some cool twists in the cosmic storyline. Picture this cosmic dance. As radiation gradually shows up, the entanglement entropy, representing the quantum connection between the black hole and emitted radiation, starts growing. Now here's the twist. Don Page imagines this growth forming a V-shaped curve that eventually hits zero at the endpoint. Imagine this curve as a roller coaster ride, reaching its midpoint known as Page time. At this pivotal moment, things flip, challenging our assumptions and exposing the influence of quantum gravity on larger black holes, way beyond what we initially thought. The analysis intensified the black hole information problem, now termed a paradox rather than a puzzle. Page's findings indicated a potential breakdown of low-energy physics in situations not traditionally associated with quantum gravity. This unexpected challenge prompted physicists to move beyond a verbal debate to a mathematical calculation, with Andrew Strominger of Harvard University emphasizing the power of precise equations in resolving such issues. Page clarified the problem, but the solution required confirming the entanglement entropy's V-shaped curve. If it aligned, information was preserved, particle physicists' view. If not, it hinted at destruction, general relativists. Despite Page's guidance, it took nearly 3 decades to solve. In the last 2 years, physicists confirmed the Page curve, signifying information escape. The journey began with string theory insights and eventually evolved beyond it in recent papers. In October 2018, Ahmed Almheri kicked off important work on black hole evaporation. He teamed up with colleagues using a concept from Juan Maldacena in 1997 called ADS-CFT duality. Think of it like a snow globe. Inside, it's our universe with gravity, while the boundary lacks gravity but is full of quantum physics, reflecting the inside's complexity. In the ADS-CFT framework, black holes on the boundary have partners in the bulk. Despite not naturally evaporating, researchers found a way by introducing a steam valve mechanism. This adjustment allows them to simulate black hole evaporation. To understand the process, they used a refined concept called quantum extremal surface, like a soap bubble in the bulk reflecting quantum-influenced geometry. This surface links bulk and boundary, correlating area with entanglement entropy. In studying evaporating black holes, they noticed something unexpected. Initially, entanglement entropy increased, aligning with Hawking's predictions. A surprising twist occurred. A quantum extremal surface appeared just inside the black hole's horizon, leading to a decisive drop in entropy. Researchers likened it to a phase transition, signaling new physics beyond Hawking's calculations. This change split the universe into two parts, one like the boundary and another, unaffected by the boundary's info, raising questions about radiation impact. The key, the quantum extremal surface sat just inside the black hole. As it shrank, so did entanglement entropy, forming the expected downward slope predicted by Page. This marked the first time a calculation showed this outcome. By confirming entanglement entropy aligns, the team showed black holes release information, though highly encrypted by quantum entanglement. This encrypted state makes it seem like the black hole hides info. However, as it reaches a tipping point, the information becomes decryptable. Despite simplifications, researchers argue these principles should universally apply. In August 2019, Almheri and team discovered something intriguing. Imagine the black hole as a central hub with radiation flying out. However, equations suggest that with time, particles deep inside the black hole join the escaping radiation, creating what they call an island. This unexpected shift in arrangement plays a role in decreasing entropy, leaving scientists with a new puzzle even as they confirm information retention. Hawking's ideas explored space-time, forming shapes like donuts or pretzels, giving rise to cool things like spatial wormholes or mini-universes. New black hole analyses dig into these exotic shapes. To simplify, researchers focused on key shapes called saddle points, which are like calmer geometries for evaporating black holes. They used a math tool called the replica trick to calculate entanglement entropy. Think of it like checking a coin's fairness by tossing replicas, a clever way to judge entropy without all the details. This trick has a physics basis. It treats replicas and real black holes alike, activating hidden shapes with multiple black holes linked by wormholes. The competition with a regular single black hole leads to a quantum transition, a big discovery in the analysis. In November 2019, physicists from the West and East Coasts used the replica trick to confirm the Page curve, showing that radiation carries away info from a black hole. String theory isn't essential, making it accessible to critics. While details of how info escapes are unknown, they explored an intriguing idea: feeding the radiation into a quantum computer to simulate the black hole. Surprisingly, the high entanglement between the radiation and the original black hole made the quantum computer link to the hole in the simulation. This link acted like a wormhole, connecting the simulated and original black holes. This aligns with a 2013 proposal by Maldacena and Susskind, suggesting entanglement as a conceptual wormhole for info to escape. With uncertainties in different proposed calculations, some doubt there's a solution within current theories. Different models suggesting stringy effects that prevent black hole formation have been suggested. While recent work calculates the Page curve and hints at information escaping black holes, it doesn't fully explain the whole process. The black hole information puzzle is partly solved, but understanding black holes more broadly is still a complex journey.